Good morning, good afternoon, etc. Looking at another Math Minute today and another question from our St. Eunan's College in Letterkenny entrance examination from 1913. Are you as smart as a high school freshman from 1913? Let's find out. We're going to dive into kind of a weird rate question. I say kind of weird in that it's dressed up in a little bit of a strange manner, and the numbers are probably going to seem a little bit strange to a modern student, but this is definitely a basic rate times time question that a modern 8th grader could be expected to do. Let's go ahead and take a look. 16 men and 10 boys reap 15 3/4 acres in 12 days of 10 hours each. How many acres would 33 men reap in 63 days of 7.5 hours each if 3 men reap as much as 5 boys? So the first thing that stands out to me here is that we have lots of different units or dimensions in this problem. We've got men, boys, days, hours, and of course, ultimately, the question is asking about how many acres do we reap. So the first thing I want to do is start to get some of these units the same. I need some more common units here. I don't want 5 different units for this question. One easy thing is that we can convert between men and boys. We're told 3 men essentially do the same work as 5 boys. And so up here, when they tell me about 10 boys working with the 16 men, I think to myself, well, those 10 boys are equivalent to another 6 men. So in fact, this question is about 16 plus 6 equals 22 men and what they're accomplishing initially. The other thing, of course, is that we've got different days of some number of hours. So let's just convert that into hours right away. The initial work was done in 12 days of 10 hours each. So obviously that's 12 times 10 equals 120 total hours. And then one other thing we're going to want to do here is make sure that we've converted all these mixed numbers, which are kind of annoying to multiply and divide by, into improper fractions. So of course, 15 times 4, if we're thinking about a common denominator of fourths, is 60. 60 plus the 3/4 that we already know about makes for 63/4 acres that the men and the boys initially reaped. Now this takes us to our actual question. We want to know how many acres do 33 men reap in 63 days of 7.5 hours each, but in some sense, and this is the key, at the same rate that the 22 men who worked 120 hours each. It's tempting to set this up as a proportion now, but there are 2 problems with that. One, obviously we have 3 quantities, acres, men, and hours, whereas a proportion needs just 2 quantities. That problem's not impossible to deal with, but even then I think it's going to be better to set this up essentially as a dimensional analysis question, where I'm just looking to cancel out units and make sure that I have acres at the end of the problem. The way I'm going to do that is I'm going to remember my rate times time relationship. This relationship pops up in a lot of different scenarios. Most typically, distance equals rate times time. But a rate times a time can actually be anything. It just depends on whatever the units are in our numerator. Yes, if I'm looking at a rate that's in miles per hour, what gets accomplished is some distance as measured in miles. But in this case, if I'm looking at a rate in terms of acres per some amount of time, what gets accomplished is the work of reaping the acres. So I'm going to take those 63/4 acres, and I'm going to think of this as a rate. I'm going to divide that up over the amount of time. We had 22 men, and each one of them was working 120 hours. That's the other key to this question. We're essentially looking at an amount of time in terms of man hours. If I have 2 men working 10-hour days, that's 20 total hours available for work. So I'm multiplying the number of men times the number of hours. I'm going to do the same thing here with my 22 men and the 120 hours each one of them works. Because I'm approaching this as a dimensional analysis question, I can see now, to cancel out those men, I'm just going to put the 33 men in my numerator now. Those are the 33 men who are working on the new number of acres that I'm trying to solve for, and having men in the numerator is going to cancel with the men I already had in the denominator. Of course, I also need to think about those 63 days of 7.5 hours each, in other words, per day. And so the days are going to cancel right there. And the other thing I want to be doing is remember, everything in this question, it's better to have as an improper fraction rather than a mixed number. And so I'm going to write that 7.5 hours per day as 15/2. At this point, you can tell all the units have canceled except for acres. So I can now do the calculation, and I know that this answer is going to be in acres. So I'm going to go ahead and rewrite this with all my denominators in the denominator. So this 4 from the 63 goes down. 33 and another 63 stay up top. 15/2. The 2 goes down to a denominator. And of course, I have those original numbers that were already in the denominator, 22 and 120. At At this stage, I think to myself, have I done something wrong? Because it seems more likely that that early 20th century math teacher meant for me to cancel out these 63s. Should it be the case that I was actually dividing by one of them? But because I've done the dimensional analysis and I know that the units are canceling out properly, I don't think that these 63s are supposed to cancel. I actually think that 63 squared is going to end up being involved in this calculation. Maybe we'll be able to do something special with it. We'll see in a second. Obviously, we want to cancel whatever we can cancel. 33 and 22, for example, both have 11 as a factor. 11 goes into 22 twice. 11 goes into 33 three times. 15 actually goes into 128 times. But at this point, I think all we have are 2's in our denominator in terms of the factors, and all we have in the numerator are 3's and 7's. So I don't think we can do any more canceling. But I do notice right now, 4 times 2 times 8 is 64, and 64 is awfully close to 63, suspiciously close. So I'm actually going to rewrite the calculation now. In the numerator, 3 times 63 squared. In the denominator, 2, that's this extra 2 over here, times the 64, that again came from the 4 times the 2 times the 8. So why does that matter? Why does it matter that we have a number that's not cancelable, not factorable? 63 and 64 don't share any factors in common, but they are quite close. Well, having the 63 and the 64 means that we get to take advantage of a particular division pattern. You wouldn't necessarily call it a factoring pattern. Well, maybe I will write it algebraically so that you can see. So what we're going to do is we're going to take the 3 over 2 and just kind of shift that to the front. And then what we want to do here is think about what on earth is 63 squared divided by 64. In general, imagine I wrote it this way instead, n squared over n plus 1. You can see in this particular case, this is the same as what we had a second ago with n equals 63. n plus 1, anytime you see that, that should make you think of what's called a difference of squares pattern. A difference of squares pattern works this way. Let's say that I write that not as n squared, but as n squared minus 1. Now, of course, n squared and n squared minus 1 aren't the same thing, so to be allowed to do this, I also have to put a plus 1 out here. And now I'm going to section this off into two different fractions. I'm going to call this n squared minus 1 over n plus 1, and then 1 over n plus 1. So this is equivalent, and if we added it back together, the plus 1 and the minus 1 would cancel to 0. They would add up to be 0, and they would get us back to that n squared. But the reason why it's nice to have it written this way is I can now take a look at n squared minus 1, and I can factor that as a difference of squares pattern. N squared is obviously a perfect square, but 1 is also a perfect square. And in fact, this always factors as n minus 1 times n plus 1, meaning those n plus 1s now cancel. Now I have a common factor. This would be like making there have been a 64 in that numerator. It turns out that 63 squared is the same thing as 63 minus 1 times 63 plus 1 plus an additional 1. We can verify this real quick in a calculator. 63 minus 1 is 62. 63 plus 1, that's the 64 we want to be able to cancel, and then the whole thing add 1 to get the proper value, and you'll see that is indeed the same thing as 63 times 63. You can see that that means what we end up with is n minus 1 plus the fractional part 1 over n plus 1. And that's the same thing as the thing we could not cancel, the n squared over n plus 1. Back over here, that means our 63 squared over 64 can actually be written as 63 minus 1 plus 1 over 63 plus 1, which of course is our denominator 64. So this is really the same thing as 3 over 2 times 62 and 1/64. At this point, we essentially want to treat this like a distribution. We're going to distribute 3 over 2 to the 62 and to the fractional part 1/64, because of course a mixed number is really a statement of addition, and that's going to give us our final answer. 3 over 2 times 62 plus 3 over 2 times 1 over 64. 2 goes into 62 31 times 3 makes 93. 3 over 2 times 1 over 64 makes 3 times 1 is 3 over 2 times 64 is 128. And there you have it. That is our final answer, 93 and 3/128 acres. So what on earth is this testing, right? Why would this be on an entrance exam in 1913? The context obviously kind of makes sense. Presumably farming was big around Letterkenny in the early 20th century. But of course, we give pseudo-context to problems all the time now in math textbooks. We'll write random word problems that talk about cell phone rates or purchasing apps on an app store. We even still obviously do car problems, miles per hour. A certain car drives this direction, another car drives that direction. An airplane goes this direction, an airplane goes that direction. So the fact that the context happens to be about reaping some crop from a field, it doesn't seem terribly important to me. Instead, this tells me that proportional thinking, the ability to think about rates and how those rates play out over a certain amount of time, was just as important 100 years ago to some 8th grader as it would be today. Again, this is definitely still in 8th or 9th grade math content in the United States. So for a problem like this first one, which if you didn't see, this is the second in like a series of videos, I'll put a little card up here where you can go back and click on that first video. This first problem, you really wouldn't expect an 8th grader to do anymore because we can just type it into a calculator. But some forms of math reasoning don't change. We still expect our students to be able to engage in proportional reasoning and answer those sorts of questions. Are you as smart as an 8th grader or a 9th grader from 1913? Probably so. You know, statistically speaking, you're probably a little bit smarter, but more importantly, you're absolutely as able as some 8th or 9th grader from over 100 years ago to engage in reasoning. And this question is testing reasoning, just with a context we wouldn't normally use today. I hope you found that interesting. If so, like and subscribe. Let me know, are there other questions like this you've seen some other entrance exam you want me to take a look at? I'd be happy to do so. Comment down below, and otherwise I'll see y'all next time.